the initial concentration. Okay? That's a big thing that it's easy to miss. And then it's simply solving an ice table as you normally would. All right? Okay. Common ion effect is going to come back into play later on in chapter 17 when we talk about solubility. And you can kind of see why. It's going to just force our equilibrium to go the opposite direction. Other questions? Okay. All right, then let's go on to buffers. How many of you have used a buffer? Couple few. Okay, so a buffer, well, you're all using buffers because there's, your blood is a buffer, so that's kind of a technicality. So buffers are a substance that resists change in pH when a number of things happen. Either you dilute it, when small-ish amounts of acid or base are added, or when the temperature is changed. Okay? And what we find with the buffer is that we need to have a solution that contains a weak acid and the salt of its conjugate base, or the weak base and the salt of its conjugate acid. Okay? In any case, you need to have a conjugate acid-base pair. And there's going to be two equilibria in play in the solution. Oftentimes we're going to sort of abbreviate that as one equilibrium. But in reality, we're adding two different things, so we can think of it as two equilibria. So we'll have our weak acid, which we can abbreviate HA. We're going to add that to solution, and it's going to be in equilibrium with its conjugate base and H3O+. We're also going to add the salt. So here we're adding the salt of the conjugate base of the weak acid. So in this case, A-, or as I've written over here, NaA, which is the sodium salt of the conjugate. And that's going to be in equilibrium with HA and OH-. So these two equilibria are taking place. So let's look at specifically. Let's make a buffer by mixing hydrofluoric acid, HF, and sodium fluoride, NaF. We know that sodium fluoride is going to completely dissociate to form the sodium ion and the fluoride ion. The sodium ion won't affect the pH, but the fluoride ion will, and that's given by our second equilibrium, F- plus H2O, in equilibrium with HF and OH-. And HF is going to be in equilibrium to form F- and H3O+. All right. So let's say we add a strong acid to a buffer. We're going to add HCl in this case. And that's going to completely dissociate to form, we'll just call it H+. Which species of these two, HF and F-, which species is that H+ going to react with? Think back to how we looked at predicting the pH of a salt solution. Kind of ties in there. So our acid can only react, in this case, with the fluoride ion. And it's going to form HF. There will be an equilibrium, though. So let's go back. Let's put our back arrow in there as well. Okay. Everyone see that? It's not going to react with HF because if it did, it would form H2F, and that doesn't exist. So you kind of have to be familiar a little bit with the chemistry, and that's related back to predicting structures and things like that. Okay. So what happens when we add sodium hydroxide to the solution? OH minus is formed, and it's going to react with our weak acid, HF. And it's going to form water and F minus. All right, so let's go back here. So when we add a strong acid, it's going to react with the conjugate base. Or the weak base in this case, and the strong base is going to react with the weak acid. Okay, so that sort of hopefully will help you simplify what's happening. So the other thing I want you to note is that and this is kind of a circular idea here. So when we react hydroxide with HF, we form F minus. But what does F minus do in solution? It has an equilibrium with water and forms HF and OH minus. So one of the things about buffers that's really unique is that it resists a change in pH. And this is why, because when we add a strong acid or a strong base, let's just talk about the strong base for right now. We add the strong base, reacts with the weak acid and forms the conjugate base. But that conjugate base is going to re-equilibrate with water and reform some amount of HF. Okay? So this is part of the reason why buffers are so good at resisting a change in pH. So let's look at this in terms of concentration. So we've got a buffer here that's going to contain acetic acid and acetate ion, probably in the form of sodium acetate. So the weak acid is pink, the weak base is blue. When we add hydroxide to solution, what forms is acetic acid is going to react with hydroxide. The concentration of acetic acid is lowered. The dotted line represents where we were. Okay. And the concentration of the acetate increases. Okay. So the acetic acid plus hydroxide forms the acetate ion and water. When we add acid, the acid is going to react with the acetate ion. So we're going to see less acetate ion, and the concentration of acetic acid increases. And in terms of a pH change, when we add base, we do see the pH increase. And when we add acid, we see the pH decrease. Nothing surprising there. And you can even see that in terms of the relative concentrations of weak acid and conjugate. More acid, less base. Okay. I'll say though, after these reactions happen, there's no more H3O plus left in solution of significance. It would only be from the autoionization of water that was taking place. So this completely reacts. Okay, no more H3O plus, and then no more OH minus. Okay, that's important. Because when you do titrations and things like that, you need to be thinking about the fact that those are completely reacting away. Speaking of titrations, this is a small portion of a titration curve. I know we haven't talked about titrations yet. Have you done one yet in lab? pH titration? Not a pH one. You did something with solubility, I think. Yeah. nightmares, right? So what this plot is showing is how the pH changes with addition of base or with addition of acid. Okay. So the middle line here represents no addition of acid or base. And when we add some base, we see the pH increase. Okay. Increases slowly until all of a sudden it's skyrocketing. Okay. If we add acid, it decreases slowly, pH decreases slowly until eventually it will decrease drastically. And what's in the block here is a region it's called the buffer region. It's where there's very small changes in pH. So what this is telling you is that, yes, a buffer is good at resisting changes in pH when acid or base is added, but it has its limits. Okay, and that's based on the mole ratios of acid and weak acid and conjugate base in solution. So if we were to draw a plot of pH change versus moles of acid or base added for water, we'll say this is 0 moles of acid added. We'll add moles of hydroxide, moles of acid, hydronium ion. Initially, if we have just water, pure water, our pH will be 7. Okay. When we add hydroxide, we will see the pH increase quite quickly. And when we add hydronium ion, the pH will decrease quite quickly. Okay. So you'll notice the difference. This is a linear change here with pH and in water when you would add moles of hydroxide or moles of acid, but it's not the case in the buffer region for a buffer. All right. So those are the main differences between buffers and solutions that don't have buffering properties. The other thing to note here, because this is going to come back, so where we are in terms of pH initially for our buffer is around maybe slightly less than 5-ish. This is, knowing the textbook, is probably the acetic acid acetate buffer. So whenever the pH starts out initially at less than 7, you have a weak acid buffer. Okay, so there's probably acetic acid acetate. We'll come back to that. We're going to talk more about that when we talk about titrations. So there's a property of buffers that's called the buffer capacity, and it's just the amount of acid or base that can be added before there's a large change in pH of the solution. It's dependent on a number of things. It's dependent on the ratio of weak acid to conjugate base, or conjugate base to weak acid, or weak base to conjugate acid, I guess is better to say. It's also, the best buffer is going to have a ratio of acid to base somewhere in the 1:10 or 10:1 region. The best buffer will have a ratio of acid to base is 1:1. So molar ratio of 1:1. 1 mole of acid to 1 mole of base, for instance. And when we make a buffer, the pKa for that particular acid or base should be close to the desired pH. Okay, so your book's going to talk to you a little bit about those types of things. For instance, because I see this acid all the time, the pKa for acetic acid acetate is 4.76. That's not acetate. So if you wanted to make a buffer that was around 4.5 or maybe 5, you could pick acetic acid and acetate as a good buffer combination. Okay? You wouldn't pick acetic acid or acetate to make a buffer at around pH 7. Okay? That's not going to work very well there. And part of this has to do with the fact of the ratios that you're going to need for acid to base. If you put more acetate ion, more weak base in solution, your pH is going to be more basic. Okay? And if that is the case, if more base is present in solution than the acid, would you expect the buffer to be more resistant to strong acid or more resistant to strong base? So you've got more weak base in solution than weak acid. In that case, you could add more strong acid to the buffer than you could add strong base before the buffer breaks down. Okay? So when you measure buffer capacity, this is something that we do in the quantitative analysis course. When you measure the buffer capacity, you get different numbers for various buffers depending on if you add strong acid or strong base to actually measure the buffer. So it's not a perfect calculation, but it is a very useful thing to know. It gives you a sense of how good of a buffer you've created. All right, so let's actually talk about calculating the pH of a buffer. Here we go back to our acetic acid acetate. There's a lot that's going to happen in this problem, okay? So we're going to do this stepwise. First, we're going to mix 100 mils of 1 molar acetic acid with 100 mils of 2 molar sodium acetate. And we want to find the pH, and our Ka for acetic acid is 1.7 times 10 to the minus 5. So we're going to first use an ice table, okay? And make sure we, again, are using concentrations in the ice table. All right. Now, I've given you concentrations of acetic acid and acetate. So they're in two, here's our 2 beakers. Here's our acetic acid. Here's our acetate. 100 mils of each. We're going to put those in a new beaker, one at a time. And now we're going to have a solution with a total volume of 200 mils. Okay? So our concentrations that were given are actually going to end up being diluted because we're mixing these two solutions together. So you can use the dilution equation. Everyone remember this one? M1V1 equals M2V2, or MIVI equals MSVF, initial final. So let's, next slide here. So the first question that I'm going to pose here, we're going to do this stepwise, is what are the concentrations of acetic acid and acetate after mixing? And again, remember that sodium acetate, there's 1 sodium. I'm just going to write out acetate. I don't have to do that. It's CH3COO minus. Okay. 1 sodium acetate to 1 acetate, so it's 1 to 1. Okay, so let's find the concentration of acetic acid. So we have 100 mils of 1 molar, and the final volume is going to be 200 mils. Does everyone see that? So we can use M1V1 equals M2V2. You can use milliliters as long as you're consistent on both sides of the equation. You can change it to liters if you want. I know that the units technically don't cancel out on this side of the equation because I'm using milliliters, but laziness wins. I'm going to end up with a concentration of acetic acid, HA, of 0.5 molar. I'm also abbreviating, I should have stated this more clearly, I'm abbreviating acetic acid HA because it's easier to write, and acetate as A minus. Questions on that? Okay, so our concentration of acetate is going to be the, we have 2 molar of that, yeah, 2 mole per liter. We have, we have 0.1 liters of that, and how we'll switch to liters just to confuse you, and a total of 2 liters. And we'll end up with 1 mole per liter. Everyone agree? All right. So is our reaction at equilibrium? So we're going to start initially with 0.5 moles per liter of acetic acid and 1 mole per liter of acetate ion and 0 moles per liter of acid H3O plus. I already told you that in this case you most likely have to form products, but we can prove that to you mathematically. So let's calculate Q. Q is going to be equal to the concentration of H3O plus times the concentration of A minus divided by the concentration of HA. And so it's going to be equal to 0 times 1 divided by 0.5. And I end up with 0. So Q is less than K. And the reaction will proceed towards the products. All right, questions on that part? So like I said, you most likely don't need to do this step unless you're unsure of which direction the reaction is going. Let's now use our ice table. So again, I'm just going to rewrite my equilibrium. HA plus H2O in equilibrium with A minus and H3O plus. Have our initial concentration of HA is 0.5. We're not going to worry about water. Initial concentration of acetate ion of 1.00 and 0 in terms of the H3O plus. So you can see with just this initial setup on our ice table that this looks very similar to the common ion problem, which is good. Right. So you can see how these 2 sections are tied in together. The change, we know we're forming products. We're going to have minus X for HA, plus X for A minus, and plus X for H3O plus. So at equilibrium, we'll have 0.5 minus X for HA, 1 plus X for A minus, and X for H3O plus. And so we can set up our equilibrium constant expression. Ka equals 1.7 times 10 to the minus 5 equals 1 plus X times X divided by 0.5 minus x. Here we can assume, can we assume that x is small compared to 0.5 and 1? Let's look at how our 0.5 initial concentration divided by our Ka turns out. If this will allow us to assume that x is small, then the initial concentration of 1 will surely let us assume that x is small. So when you divide 0.5 by 1.7 times 10 to the minus 5, you end up with 29,000. So yes, we can assume that x is small. X is negligible. So we can get rid of x in comparison to the 0.5 and to the 1. So we'll end up with Ka equals 1.7 times 10 to the minus 5 equals 1 times x divided by 0.5. And we should end up with x equals 8.5 times 10 to the minus 6. And this is equal to our H3O plus concentration. Okay, so that's what we were asked to find. We were asked to find H3O plus and then calculate pH. So the pH is equal to minus the log of 8.5 times 10 to the minus 6. So I end up with 5.07.
Really quickly go over how you got the initial concentration.
Yeah, how did I get the initial concentrations? So, when we have the 100 mils of 1 molar acetic acid, and we mix that with 100 mils of 2 molar sodium acetate, we have a total volume of 200 mils. Okay. So now we need to figure out, using the dilution equation, the final concentrations of acetic acid and sodium acetate. Does that help, or do you need more? Okay. Other questions? Would you like an easier way to do this? Okay. On this slide, we were able to assume that x is small. That's going to be the case for almost every buffer solution that you make, because you have both HA and A minus in solution. That's the definition of the buffer. So that forces this x to be very small because of what it does to the equilibrium. Okay. The thing I did want to point out, because I didn't stress this on the last example, was, and this sort of goes back to my point that we can use initial concentrations for our equilibrium concentrations. When we calculated x the first way through the ice table, we end up with 8.5 times 10 to the minus 6. When you plug that back in for the concentration of HA and A minus, you'll notice that that value is negligible. It's beyond the significant digits. So that's how we can assume that our initial concentration is our equilibrium. Let's do that. Whoop. Okay. So there is an easier way to calculate the pH of a buffer, and that's using the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is simply derived from the Ka expression. If you really are interested in, we can talk about it. I'm not going to do that right now. But it comes from Ka equals A minus times H3O plus divided by HA. Okay, you can get that. Trust me. So what this tells you though is that you need three things in order to solve for the pH of a buffer solution. You need the pKa, and you need a concentration of A- and a concentration of HA. The other thing I want to point out is notice how, so what this is telling you, because when we normally write things in brackets, that means equilibrium concentration. If we needed that, this would be a harder problem. But because X is small, we can assume that A- here in this equation and HA are initial concentrations. Okay. So for the Henderson-Hasselbalch equation, you can put initial concentrations in for the concentration of A- and HA. That's going to make life really easy, hopefully. All right, there it is. Concentration for okay, so back to the same problem we were working on. 100 mils of 1 molar acetic acid, 100 mils of 2 molar acetate. Let's calculate the pH using the Henderson-Hasselbalch equation. We were given the Ka for acetic acid, 1.7 times 10 to the minus 5. To calculate the pKa, we'll just take minus the log of Ka. So it's minus the log of 1.7 times 10 to the minus 5. And we end up with 4.77. And we know from the previous problem, essentially, but from the dilution equation and the fact that we're mixing these two species together, that the concentration of A- is 1 mole per liter, and the concentration of HA is 0.5 moles per liter. Okay. Again, these were initial concentrations, but that's okay for Henderson-Hasselbalch. So now we can plug these in. pH is going to be equal to 4.77 plus the log of A- 1 divided by HA 0.5. And yes, I'm using concentrations here. Well, never mind, pause. Ignore that part. Okay, so I end up with 4.77 plus 0.301. And I end up with the pH equal to 5.07. Just like on the last problem, but we didn't have to set up an ice table. You like that better? So you will be given the Henderson-Hasselbalch equation on the exam. Okay, so it's only used for buffers. Okay, keep that in mind. Doesn't work for every weak acid-base problem. Question?
Can you use the 2 and the 1 in the same ratio as the initial concentration?
Yeah, so this is where I was stumbling because I didn't want to confuse you guys, but because this is a ratio, the total volume doesn't matter as long as it's the same.
Okay.
Yeah.
So you can use the initial concentrations, but if they're not given, you can use.
Well, we'll do some other problems where it's not as useful to know that. Yeah. I would recommend though, I mean it is the same ratio, so it doesn't matter. It just feels wrong to me to tell you that that's okay to use.
Okay.
And Hasselbalch. Okay. I want to do a little bit here. So I want you to start thinking about these problems. This is going to be the hardest problem you're going to work on for the exam, okay? So I want you to start thinking about this. We know that a buffer resists change in pH by reacting with acid or base. If we make a buffer with 1 liter of 0.5 molar ammonia, and 1 liter of 0.8 molar ammonium chloride. Okay, we're given a Kb value. First thing we can do is determine the pH of the solution. And then what we're going to do is add strong acid, or actually, I think we're going to, let's go back to slide 18. I want to point out one other thing. The Henderson-Hasselbalch equation you're given uses pKa. Okay? There is another Henderson-Hasselbalch equation that uses pKb. And what it does is it flips A minus and HA. Don't worry about that equation. You might come across it when you're Googling things. Okay, Henderson-Hasselbalch for a weak base. You don't need it. Stick with using this one. It's going to help clarify things for you. And you can figure out pKa given a Kb, right? So you'll take your Kb, Kb, and you'll convert that to Ka using Kw equals Ka times Kb, and then go to pKa, okay? So you can use this equation even for a buffer-based base. We'll start here next time. Now we're going to add acid to the solution. I want you to think on, this is slide 20, take a look at this and look at what reaction is going to take place. So is ammonia going to react, or is ammonium going to react? Okay, we're adding H+. We are going to end up using a reaction table. Okay, so this is different from the ice table. You may have seen it as BCA table, before, change, after. In this type of table, we're going to use moles. Okay, we're not going to be using concentration. This goes back to chapter 4, I think, something like that. After we do that, after we react our strong acid with our buffer, we're going to go back and determine our acid and conjugate base, and then we're going to plug that into the Henderson-Hasselbalch equation.